Hello, I am Arshit Navin Lachappa. Welcome to the presentation of our project on AES 128 hardware software co-design. We implemented the system on the DE1 SoC platform, which integrates both a hard processor system and an FPGA fabric. This project was developed by myself and my teammate Arshit Mukanda as a part of the design and analysis of reconfigurable system course. The primary goal of this project was to design a complete hardware software co-design that leverages the parallel processing capabilities of the FPGA to accelerate cryptographic workloads, specifically AES 128. We divided the responsibility into two distinct domains. The HPS software handles control, validation, and key generation. It also runs a full software-based AES implementation to serve as a verification standard. The FPGA hardware acts as a dedicated accelerator. It implements the AES 128 encryption algorithm in hardware to maximize throughput. Our key objective was to verify the correctness of the FPGA encryption by comparing it against the software golden reference. Here is the high-level architecture of a system. The workflow begins with user input, which is received via UART. The HPS generates the key and controls the flow. It communicates with the FPGA using the lightweight AXI bridge. This bridge connects the processor to the FPGA core, which is strictly responsible for performing the AES 128 encryption. Once the FPGA finishes encryption, the HPS reads back the results and performs decryption and validation. This architecture ensures the heavy lifting is done in hardware while the complex control logic remains in software. On the software side, the HPS has three critical tasks: generation, communication, and verification. The generation. It generates a random 128-bit AES key at runtime and accepts up to 16 ASCII characters as plain text from the user. Communication. It sends these inputs to the FPGA via the lightweight bridge and waits to receive the ciphertext back. Verification. The HPS runs a software version of AES encryption. We use this as a golden reference to strictly verify that the FPGA output is accurate. Moving to the hardware, we designed an AES 128 encryption core using Verilog. The core interface features two 128-bit inputs, one for the encryption key and one for the plain text data. One 128-bit output for the resulting ciphertext. Control signals, a handshake mechanism for start and status signal to synchronize with processor. Internally, this core processes the data in 128-bit blocks mapped to four 32-bit registers for each input and output. The bridge between the software and hardware is the memory mapped interface. We utilized the AXI interconnects to map the FPGA's registers to specific addresses in the HPS memory space. Here is the address map we defined. 0x00 to 0x0c are the key registers where the HPS writes the encryption key. 10 to 1c are the plain text registers for the input data. 020 to 02c are the ciphertext registers where the HPS reads the result. 30 is the control and status registers used for the pooling handshake to determine when encryption is complete. To ensure robustness, we employed a two-stage verification strategy. First, we tested against the NIST known test vectors using 7 fixed vectors to confirm the hardware meets standard cryptographic specification. Second, we implemented interactive user testing. In this mode, the user enters a custom plain text, a random key is generated, the system runs both hardware AES core FPGA and the software AES core HPS simultaneously. We compare the result. If the hardware cipher matches the software cipher and the decrypted text matches the input, the test passes. So here is a summary of our demonstration results as indicated by the check marks. FPGA encryption accurately matches the software AES output exactly. Decryption successfully recovers the original plain text from the hardware generated cipher text. The system achieved a complete end-to-end verification with all test vectors passing. Now let's see the demo of how it works. Now let's open the Quartus project. So over here you can see this is our Quartus project and this is the top level model which we have defined it. Over here we have instantiated all the new inputs and outputs in this part. And this is our top module. Now I am opening the platform designer. So this is our platform designer and we have used these peripherals, and here is the AES accelerator which we have used as a wrapper where our core logic is there, which we have written in Verilog where it does the FPGA encryption. So once we are done, we will generate a HDL. Once the HDL is generated, we can compile the design. And this is our software part, which is the HPS, where it would do all the encryption and decryption. And we have also created the executable file over here, and we have also used the header file of the HPS. Now let me open the putty in order to run the Linux in our local device. So as you can see, I have turned on the board and we can able to get our Linux terminal in our own local machine. Now let's log in. The login is root. Now let me do the. Now let's detect the USB drive fdisk -L. Now let's mount this. So after detecting the USB, I have mounted the USB and opened the current working directory to access the data. Once the data is accessed, I have unmounted the device. Now let's run this. So this is the executable file which I will be running. So before running this executable file, we need to program the FPGA. This is our Quartus. Now let's program this. Let's select this device. Now let's start. It's been successful. Now let's run the software. So this is the first stage of our verification, where we tested against the NIST known test vectors using 7 FIS text vectors to perform the hardware meets standard cryptographic specification. So you can see that we have used 7 vectors and it's all passed. Now let's go to the second stage of verification, where we implemented the interactive user testing. So over here you can see that it's asking for, do you want to test your own plain text? Let's press Y as yes. Now let's enter any maximum 6 characters. I like FPGA class. See, this is my input and you can see that it's all be passed. Now let's try for another. Let me give my name. This is my name. See, it's passed. So this slide shows the actual terminal output from the DE1 SoC board. In part 1 and 2 you can see the system running the 7 NIST test vectors. For each vector it prints the expected cipher and the hardware cipher and the software cipher. The summary confirms all vectors passed. In part 3 we enter the interactive mode. I enter the plain text as I like FPGA class. You can see that the system printed the generated 128-bit key and the resulting hardware cipher in X. Crucially, the final checks at the bottom confirms both parts. This confirms the hardware is functionally correct. This is the interactive mode. These are all the 7 test vectors. If you press N, it comes out of this terminal existing. So in conclusion, we have successfully implemented and verified a complete AES 128 hardware software core design. The FPGA effectively accelerates the encryption task, while the HPS ensures robust control and verification. This system passed all functional tests, demonstrating a reliable and efficient design. Thank you.